Welcome everybody. Welcome to this new session in which the lecturer is Dr. C.K. Chou. He will talk about 5G RF safety concerns and the new IEEE C95.1-2019 safety standard. So he is the IEEE International Committee on electromagnetic safety, TC95. He's the chairman. So Dr. Sika Chou received his PhD degree from the University of Washington in 1975. From 1976 to 2013, he worked at the University of Washington, City of Hope National Medical Center, and in Motorola. He's retired and currently an independent consultant on electromagnetic field safety issues. He continues to serve as chairman of the Technical Committee 95 of the IEEE International Committee on Electromagnetic Safety, responsible for exposure standards from 0 to 300 gigahertz. So that is from DC to almost what we can work or the technology will allow in the near future. He has been from 2006 to the present. Dr. Chou received the Darsonval Medal from the Electromagnetic Society in 2006 and received the IEEE Standard Association Lifetime Achievement Award in 2020. He's a distinguished lecturer of IEEE Broadcast Technology Society, and as a distinguished lecturer, we received him some years ago here in Montevideo. So it's the second time he's with us in Uruguay. So CK, thank you for being present in Uruguay, in Urucon. The floor is yours.
Gracias, Rafael, for the introduction. Damas y caballeros, buenas tardes. Thank you, Rafael, again for inviting me to this meeting. And as Rafael said last time, I was in the university September 5th under the sponsorship of IEEE Broadcast Technology Society. After 5 years, I learned some Spanish, but not very much. So I do still have to use English to present for today. And so let's get on to the slides. And I was assigned to talk about these RF safety concerns. Of course, with any new technology, people worry because we don't understand it. And so I will use this opportunity to tell you what's about 5G and what we do with IEEE standard. How do we deal with this new application? So I'm also, I want to say I'm not speaking for IEEE. I'm just speaking as an individual. And okay, here's the outline of what we'll cover during this hour, and a brief history of all the concerns on electromagnetic energy and some key concepts and research, touch some general broad scope and some of the standards, and especially since we are IEEE, I will talk more about on C95.1. And of course, today is more on the higher frequency for the 5G applications. So what are the new limits for this 5G? And with some conclusion. Of course, this is a global issue, not just for Latin America. It's all over the world, and people are concerned about this application. So this is not a new concern from about the electromagnetic energy. It's a long history since World War II. And some of you have been to my last 5 years ago seminar. You have seen some of the picture slides, but since 5 years already, let's review it. And the first one is about radar. People worry about this big power and energy, especially the military people. And that was in the 50s, and there was a 10-year research in the United States. And then later on, the civilians worry about this high power, this radar, these antennas on the big towers, and used for radio broadcasting or TV broadcasting. That was in the 60s, 70s. Then later on, the micro ovens, the big power device, can put into the kitchen. So even the woman with pregnant ladies or little children running in the kitchen can expose to this microwave oven frequency. And so people worry about that. Then in the 80s, some police, male police, are using the radar gun, and they are, some of them have a testicular cancer. Well, maybe it's due to the radar. So there are some lawsuits and all that, but was no proof of that. And on the left picture, the power line, there was some concern about whether the high voltage power line can cause leukemia in children. And they had many years of research on that. And of course, today we are talking about more on the wireless communication relating to cell phone, from 1G all the way to 5G. Now we're talking about today. And of course, there are many base stations all over the place. And are they safe for people? Can children use cell phones and all that? And some countries already have this so-called smart meter. Uh, and and so people worry about it. And then the very big one is the wireless power transmission, and not too many people worry about this yet. But this can involve very, very high power. This is used for the wireless charging for the cars, for the buses, and they involve kilowatts power, very near to people. And now they are really dangerous. That's something coming up. Well, I have listed here a whole bunch of two different colors of the uh, different statements. And the black ones are the common understanding of people, and mainly they get from the media, from TV, newspaper, or internet, and are the black letter statements. And the green colors are the ones like me have studied this for 50 years, and this is what my understanding is. So let's just briefly go through that. So microwave radiation is very dangerous. Well, yes, I agree, but it's very high intensity. It even can kill you. And we don't have enough understanding of this effects. Well, we have studied since World War II, so it's been 70 years. Is that long enough? Some people say no. And I would say, well, we have studied a lot. So there are different opinions on that. Many reports show non-thermal effects. I'll have more to show you what we think about that, because many of them are not repeatable, or you do not have a proven health effects. And it can cause cancer and many other diseases. And many expert groups I'll show you later, there was no proof and no mechanism other than heating and electrostimulation for the wide frequency range. And many activists say, yes.
Excuse me 1 second.
Yeah.
We are the screen you are sharing has a PowerPoint, so it is in the first slide. It is the program. We are seeing the program.
It's not moving?
Not moving, yes.
Ah, that's strange.
Oh.
Well, gee. Okay, let's see what happens. Something wrong here. Can you see the slide now?
Now the slide we have all the slides. We have the PowerPoint software. You are sharing the whole software, not only the presentation.
Only the first page?
Not only the first page. We see at the left all the other ones. I mean 1 to 5.
Can you see all this?
We see all the PowerPoint itself. I mean all the PowerPoint, all the deck.
Okay, maybe why don't I do it? Can you share the now which slide are you seeing? Is slide number 4?
Now you change to number 4, yes.
Yeah. Okay, so you can see that now. Okay.
But
so
we
I'm
can
showing
see
number 4.
Yes, we can see yes, and at the left you have 1 to 5, okay?
No, this one. You see the whole thing?
No, we see it inside the program, not full screen.
Not inside, the full screen.
Inside PowerPoint. Try to share again and choose another window.
I just did that. I just came out and redo it, and it's still the same thing, huh? Okay, maybe Rafael, how about you show your the PDF I sent to you?
Okay.
So I just ask you to move that one instead of myself.
Okay. Let me. Let me.
Use the PDF.
Yes. Okay. Okay. Wait a
I just
second,
sent to you
please.
this morning. I just sent to you this
Yes.
morning.
Yes.
Yeah,
Yes. Yes. I know. I know. I have it. I have it. I'm opening it.
yeah.
I'm opening it. Let's see. I will in a moment. It's just 15 more seconds.
Hmm.
Now I am about to share it. Okay,
Okay, let's go to number 4.
fine. Here we are, right?
Okay.
Number 4.
Yes, yes. Okay, some people said, the standards are not protective enough, the activists said. But we have a worldwide expert group, and health authorities agree they are protective. And activists say, well, we need more precautionary measure to be safe than sorry. But we do have a large safety margins built in the standards. Okay, next. Okay, I borrowed this slide from the WHO for many years ago. You can see on the left side for the public health, the real danger of the exposures, the UV ultraviolet is the most severe one, the most dangerous, and the radons and the X-rays, then the electromagnetic field is the bottom. But however, the public concern is just opposite. What's happening? Okay, next. I think the root of the concern is the term radiation, because most people talking about mention when you hear radiation, they will immediately think about the atomic bomb during the World War II in Japan, and also the 3 nuclear power plant accidents. The latest one is from Japan, Fukushima. And always you go to a dentist, you have this X-ray. When you take X-ray, you have to put a heavy apron on your body to cover you to protect you, or you go to radiation therapy. Everybody worry about radiation. It's very dangerous. So you see the two very similar symbols of warning, all in yellow in triangle, and in the middle, it's a little bit different. One is the left side is the RF exposure antennas. The other one is the radiation symbol. And many people mix the two together, radiation, such as the lower part, it says radiation from cell phones for mobile phones. They use this radiation symbol. So this is totally wrong. So people mixing the two together. So we said these two definitely not as the same. And that's why IEEE, WHO, or FCC in America do not use RF radiation as the term. We try to use RF exposure or exposure to RF energy to be distinguished from radiation. Okay, so next. So some fundamentals about this difference in radiation. This is frequency spectrum from 0 hertz all the way to very high frequency to 10 to the 13 hertz, 15 hertz there. And there's a big distinction at the 10 electron volt is the photon energy on the top. On the right is so-called ionizing radiation above the ultraviolet. And below that, it cannot cause ionization in the molecule, so it's called non-ionizing radiation. So we are talking about radio frequency in the microwave range. They are millions times below this ionizing threshold. So this is a very different between the two radiations. Okay, next. So this is just in words, the ionization, does not knock the electrons out of the orbit, will not cause ionization, like to damage the DNA, like the two double helix will not damage that. This will damage that, and it's called the ionizing radiation, can cause cancer, can be cumulative effects, and all that. However, when we talk about non-ionizing radiation, including the radio frequencies, low photon energy will not cause effects like above. And only confirmed RF effects are due to tissue heating at levels well above the limits for wireless communication. And there's also no non-cumulative effects, such as diathermy has been used in the rehabilitation medicine since 1946. Used very high power, on the body, and have been treating millions and millions of people, patients, with good results. Next. Okay, now we're talking about a new one. It's called 5G. And what's the difference in 5G from the old 3G and 4G? You see now many antennas outside use the so-called macro base stations, and they usually go 360 degrees broadcasting to all the environment. And for the 5G, you still have the macro 5Gs, like the lower right there, you see the antenna pattern. They use this beam steering or beam forming method. They only scan to the users. When they are using it, they have the signal go to that direction only. And the other place, they don't use it. They don't waste energy to shooting all over the place. So that's the difference between 5G macro and the 4G macro difference. The other difference is for 5G, you need because even in the future, for the higher frequency, you need the smaller cell going to even a street light or inside a house. For next slide, you will see. You see in the even like a Wi-Fi going to every building, every house, you can have the this small cell coverage. So now you see more antennas. The people worry there are more antennas, must be worse, right? But it's really not the case. You have to understand what's the intensity of involved. So we will see that more later. Okay, here's just another cartoon to show the difference between 4G on the left and 5G on the right. You see the 4G, go all the directions, and everybody use it or you don't use it, you get exposure too. But for 5G, use the beam steering. Only the ones that are using the phones get the exposure. So in terms of time averaging, the overall exposure will be much less. Okay, next. So we don't understand about anything, then what do we do? So as a scientist, what we do scientific research. And then you do research. After that, you publish, put it in the journal. Now it's all in the cloud, in the database. And then the committee, such as IEEE, will take all these different publications and analyze and compare and do all kinds of discussion. And we finally come up consensus standards. And regulators such as American FCC, they will adopt some of the limits, and as a government regulation to implement that. And this whole process is a continuous improvement. And whenever a scientific more research updating, we can update the standard, update the regulation. Next. So how do we study? So in terms of all the scientific study, there are four categories. One involves a large population of humans called epidemiological studies. And the second, you put people in the lab. That's called human studies. And then you don't use, that you can use animals. Animals have a shorter lifetime. It's easier to manipulate. And there are other people using in vitro studies, expose animal cells or isolate tissue in the cell cultures and dishes. So with all these four different ways of studying, the WHO, the International Agency for Research on Cancer, they put the highest weight to the first one, and the in vitro study as the least weight in terms of evidence for the understanding of any effects. Okay, next. In terms of a database, and we have IEEE as a database, and we have accumulated so far 8,000 some papers, and more than 4,000 are related to the biological effects of RF exposure. Many others are relating to the engineering measurements and other stuff. So we have more than 70 years of data accumulated in there. Next. So what the WHO says about the current understanding on this subject, and you can find this quote in this web link there. And the scientific knowledge in this area is now more extensive than most chemicals, and current evidence does not confirm the existence of any health consequence from exposure to low-level electromagnetic fields. What do you mean by low level? That low level means below the current international exposure guidelines. Okay, next. Okay, here is the very key slide here. Why we have so much controversies in this field. And this is all related to the quality of science. And it's a debate between the established versus possible effects. And that to me is a facts versus opinion. What are the facts? Facts are the you see here in the middle, they are A to F. It's like at the university, you have a class of students. At the end of a class, the semester, you give students some A's, very good students, some B, some C, some D, oh, some even flunk out. So the same is all different qualities. And the A ones are the really confirmed, established science. No matter what you do, the good science is never outdated. That's the facts. No matter what you do, it's always true. That's the A. Then you have a B. There are some studies, but well, not really confirmed, but maybe useful. We don't know. And they are unconfirmed. It contradicts to A. Something really strange here. Why is that? And there are, in this field, there are many flawed papers with many artifacts. They are not real. They are something wrong, but they got published. And there are many so-called junk reports, and they are even not reviewed. They just go on the newspaper directly without going through any reviews. So all these are we call it non-confirmed called opinions. So this is a fighting between opinions and facts. Depending on which group of papers you believe, you have a very different opinion about what's going on about this safety concerns. Okay, next. Okay, I just to share with you my experience in this field since 1971, and was a graduate study student at the University of Washington. I later on continued to work on biological related projects at City of Hope. I've used all these animals, including humans, on this, for in vivo studies. So there are all kinds of species, strains, the sex, the ages, and how do you extrapolate from animals to humans is a big thing. And also I have done in vitro study using monolayer cells, suspension, the tubes in culture and different vessels and isolate tissues. And how do you extrapolate from in vitro to go to in vivo on animals to humans is another big step. Okay, this is biological complexity. And there's another one, next slide, is on engineering complexity. Next. And also at the University of Washington, also Motorola, they are experienced on the exposure systems. You can have all different kinds of exposure system, but different energy can go into the tissue. And I show some examples on the right. And the bottom one, you see the E field, magnetic field, the same human model. When you expose to E field, it's this energy pattern. Go exposed to S field, is this heating pattern. It's totally different. So there are far field issues, near field issues, the symmetry, the resonance, or what kind of modulation, what kind of experimental artifacts, temperature controls. They are beyond many biologists' understanding of this engineering complexity in this field. So I did write a tutorial article published in 1996, bioelectromagnetics. Oh, by the way, I have all the slides already. For anybody interested in Rafael, you can send them a copy of my this PDF. Okay, so you don't have to worry about writing down the notes. Okay, next. So with all that, the biological and the engineering complexities, and here's a cartoon from Gary Larson from Seattle, and you see the Vikings are saying, why are we making circles in the ocean? Because if you have an imbalanced research ability in either biological science or engineering expertise, you will make this try to go to somewhere very difficulty because of this mixed complexities. Okay, next. And with all this research and over so many years, and IEEE has this website. You go to this link here, you will find currently there are 88 expert reviews from the either the expert groups or the governments. The latest one is showing the example on the upper corner, right corner side there. And in general, all the 88 come to the same conclusion. Is one conclusion is in the red color. There's no adverse health effects have been confirmed below the current international RF safety guidelines or exposure standard. That means ICNIRP and IEEE. I'll explain more of this later. Okay, what are the kinds of standards trying to protect all humans? The first group called exposure standards is a human is a subject and what kind of RF sources can affect our body. And they are in generally the two different levels of protection. One for the occupational group. in a controlled environment, or we call it the restricted environment. The other one is for general public, anybody in. There are two different. Second kind is the so-called assessment standards, is to limit for compliance from base stations, and they have a measurement standards, computational standard to regulate that. And it's about the interference standard about medical devices. You don't want to cause a problem, and with for human health. So today we mainly will talk about only the briefly mention the second kind. Next. So who has the ability to set the exposure standards for humans? One group is called ICNIRP, International Commission on Non-Ionizing Radiation Protection. And this is a group of about 14 experts, but they don't have any industrial representatives. And they are formally recognized and also promoted by the WHO. And the second group is us, the IEEE, called International Committee on Electromagnetic Safety, TC95. So we are a large group. It's open to anybody with interest can join us, open committee. And so currently we have about 29 countries with 130 members, are either our members or observers. And we are totally open. We welcome anybody from Latin America can also join us. Next. So IEEE, we have this from the IEEE Standard Association Standards Board, and we have the SCC 39, that's ISIS, and we have two subcommittees down below, and one is TC95 for exposure standards, and there are 6 subcommittees, and product standards for TC34. There are 2 as subcommittees, one on experimental, one on numerical standards. All our mission is to promote safe use of electromagnetic energy. Okay, next. Okay, this is a brief history of this IEEE safety standard C95. And this is actually very long history. The first one came out in 1966. And that was only a little bit more than a page standard. And it's a flat 10 milliwatt per square centimeter. It goes from 10 megahertz to 100 gigahertz, a flat standard. It's based on a simple thermal model. And over the years, in a big major change was 1982. My professor, Bill Guy, he led the change to incorporate the symmetry. So made the exposure limit frequency dependent across the band. And then we had a 1991 became 2-tier standards. And 2002, we added a low frequency standard for including electrostimulation. And 2005, I led the revision to change that into in 2005. And the latest one we have published is the one we're going to talk about more today. Is the 2019 version. It covers the whole frequency band from 0 to 300 gigahertz. Next. Okay, in this scope, and what we do is the standard specify exposure criteria and limits to protect against established adverse health effects in humans associated with exposure to this electromagnetic fields for this frequency range, and mainly to protect against 2 well-known established effects. One is for low frequency, is on electrostimulation below 100 kilohertz. The other one above that is on tissue, local or whole body heating. Next. So here's a list of severity of from 1 to 6 of the known adverse effects. And let's see, what are the real known adverse effects? It's above the dotted red line, the shocks. For example, you see on the right, a person wearing shoes, but he was too close to a energized high power RF and caused the RF burn of his big toes. See, it's a pretty severe burn there. And you see the next picture is you can draw a big arc from a 50 kilowatts AM tower. And if you touch that by hand or you touch on your leg, it's going to burn a big hole on your body. So this is all very severe cases. Yeah, see a big sparks going through there. Yeah, okay, let's go back. Then here I have surface heating. No, not yet. Go back. surface heating effect or whole body heating effect. And we don't think the micro hearing effect. I spent my half my study, graduate study on this. How can you hear microwave radars? And that's a very weak effect, and it's a biological effect, but we don't think it's a health effect. So we draw a line there. And the last one is a low level effect. I used to be called non-thermal effect by many other people. People still calling it non-thermal effect, but we call it the low level effects. And okay, what's the more about a low level effect next? And in our standard, page 107, we said the low level effects, this is the no adverse effect have been established for low level despite 70 years of research. And what about many people reporting that? Well, because there's no known international mechanism, no meaningful dose response relationship. So all the effects, reported effects, remain speculative, and they are not appropriate for standard setting. We're only talking about established health effects. And this is unproven and still not understandable, and we cannot use that as a standard setting. Next. So in terms of 5G, and of course, when we have our revision for the 2019, and we have a look at all the data published between 1948 to 2017 December, and we especially pay more attention to the from 6 gigahertz to 300 gigahertz for the higher frequency for the millimeter wave applications. We look at all the effects papers, and we have a sample in the annex C.8 on the review of literatures for this frequency band. And next. So when we talk about the higher frequencies, look at the RF penetration. The engineering term is called skin penetration. And from low frequency, 1 megahertz, all the way to 100 gigahertz, you see a big drop in terms of from 90 centimeter and 1 megahertz all the way to almost zero. And we have a big arrow there, 6 gigahertz is what we are talking about. What are the effects on body? Okay, next. So here is the just selected the frequencies. You can see the skin depths and change from 6 gigahertz as 4.09 millimeters and down to 300 gigahertz to 0.14 millimeter. Okay, next. And if you look at the from the skin cross section, and in the skin you can see the white line is a 94 gigahertz penetration depth. The 35 gigahertz is a little bit deeper into the skin, as an example. Next. So here I have a picture from a book, and this man is holding his own skin, and the skin is the largest human organ in the body. Okay, it's larger than anything else in the body. And here, okay, next is the skin in detail. And I got all the next few slides from Dr. Mamziskin. Here is the see the detailed structure. You see the very thin skin and a whole bunch of very complicated biological the sweat gland, the nerves, and the vessels and all that. It's all in there. Okay, next. So you see some on the skin, the epidermis. They are even called with 5 layers, from horny layer to basal cell, and of different thickness and different water content. There are people who have studied that before. You see the lower at 4 and 5, they are 72% mainly of water. Okay, next. Now the skin thickness on the body, it also varies depending on where it is. You know, the thinness is on the eyelid, and the thickest is the sole, the bottom of your feet. And also for male and females, they are different. So men have thicker skin than the females. So that's a proof right here. And you see the on the average, man has a 223 micron, and a female has only 180 microns. And the bottom of the feet, you know, can be almost 800 microns in the males. So it's varies in the different locations on the body. Okay, next. If you talk about the babies from the over the age on the skin, for a little baby, they are completely formed at the birth, and their skin is very thin, and there's a lot of high water content. That's why babies are so soft, so moist, and so cute to you want to pinch them, and is very thin compared to the adults, and their production of wet is very much reduced at baby's time. The next is when you start growing. Next. And even to 1 year old, the skin of a child is essentially the same as an adult. That's interesting to know. Even a 1 year old child is already as good as adult on skin. Next. Now, when it gets real old, when I get older age, like me now, and what you do is the epidermis become very thin, the blood vessels and they become very fragile. The oil production decreases, so you get the dry skin getting itchy, and the fat layer becomes very thin, so you have decreased ability to maintain your body temperature. Your sweat production also decreases, make it harder to lose heat. So that's why many older generation can die during the heat stroke, heat waves. Yeah. Okay, next. So, in Dr. Ziskin lab, they have studied a lot the Soviet or the Russian method of using millimeter wave for therapy. They have been used for many, many years in China too. And here I have three usual frequencies they use for the millimeter wave therapy: 61, 53, and 42 gigahertz. And they have mainly exposing the acupuncture points and also forehead, also sternum or big joints or surgical wounds to do the therapy. Usually 15 to 30 minutes as a session, one session per day, 10 to 15 sessions per course. So this is how they have been doing for many, many years. So next, let's see the intensities. And when the nerve from this therapy, if usually they use like 100 to 200 watts per meter square for therapeutic exposures, and you don't really feel too much heat unless you go above 350 watts per meter square, and you don't really feel pain unless you go to 1,000 watts per meter square. This is from the basic clinical experience from millimeter wave exposures. Next. So millimeter wave exposure, like you said, is a major mechanism is the heat. And most energy is absorbed within a few tenths of a millimeter. And a wave in tissue are comparable with biological structure. The exposure usually is frequently in the very near field. When you put the applicator very near the body in order to cause enough exposure for the millimeter wave effect. Okay, next. So in terms of causing pain, there are physiological temperatures. And in the normal room, we usually have a skin temperature slightly below body temperature, like 34 degrees C. And when you have a pain threshold, I have done many years of hypothermia research at the City of Hope, and we know if you go to 44 and 45, you can start causing pain in the patients. And then the next three numbers are the first skin degree burn, second or third degree burn. You have to go to 70 degrees C to cause third degree burns. Okay, next. So we have three major contributors: Dr. Ken Foster from University of Pennsylvania, Dr. Aki Hirata from Nagoya Institute of Technology. He also served on the ICNIRP, and Dr. Marv Ziskin, he's a real doctor from Temple University. They are all on our IEEE committee. And these the new limits are particularly thanks to these three gentlemen. Next. Okay, here are the new limits. How do we derive that? And we have set a maximum temperature rise less than 3 degrees in the skin for the upper tier for occupational exposure. So divide by 5 for the lower tier for the general public is the maximum is 0.6 degrees C. So that's a very small temperature elevation on the skin. So for IEEE, we use a new term called the symmetry reference limit. This is the absorption inside the body, not outside. So we call it on the very superficial layer of the skin, we call epithelial power density. And for the outside, you can measure with the instrument. It's called exposure reference limit, ERL, is the incident power density. So we can have all the limits defined there. I'll show you later. And we have an averaging time for 60 minutes for local exposures, and the averaging area 4 centimeters square. But for single pulse at the very high frequency, above 30 to 300 gigahertz, we drop it down to even average over 1 centimeter square. So all that thing in the details are in the standards. Next. So for 5G communications, and currently there are 3 bands applications. One is called a low band. It's between 600 to 900 megahertz. The range and coverage area is very similar to the current 3G and 4G towers. And for the mid band, that's mostly today are using this mid band as from 2.3 to 4.7 gigahertz, and can be up to several kilometers in radius coverage. But now it's still developing. It's for the high band. It's for 24 to 47 gigahertz. Mainly it's talking about 24 to 29 gigahertz. And this is very limited range. That's why you need these small cells and all that. But you have to only for, probably more practical, can only for dense urban environments and areas where people are congregated, such as sports stadiums or convention centers. And this can be more applications in that for that range areas, and not for really for very countryside to cover too big area. So these are the 3 existing one and the future 5G applications. Okay, next. So I just show you a whole bunch of tables. You can see all this in the standard. I just show you some of the what we are talking about. This is the DRL, the symmetry reference limit inside the body. For the low frequency, for the existing phones, even the 5G mid-band, we use the SAR, specific absorption rate. The middle one is for the general public, and the right one is for the occupational standard. That's 5 times higher to the general public. For local exposure on the head or body is 2 watts per kilogram, average over 10 gram tissue. And for the extremities like limbs, or the ears, the pinna, we have a relaxed limit by 2 times. Okay, that's for the lower below 6 gigahertz. Next. For the higher frequencies, above 6 gigahertz to 300 gigahertz, we said the DRL, now we change to epithelial power density inside the body. And for the general public, it's 20 watts per meter square. For the upper tier general restricted environment workers, they are 100 watts per meter square. So all the details are in the footnotes here. Okay, next. And they are the whole body heating from the whole RF range from 100 kilohertz to 300 gigahertz. And we have a big change from the previous standard. And also IEEE did the same change as us. Is the averaging time on the right side. It's 30 minutes. It used to be we have 6 minutes for different exposure, but that's all revised in the new standards for both IEEE and the IEEE 2020 guidelines. We all harmonize to say for whole body exposure, we average over 30 minutes, and local exposure average to 6 minutes. So this is for all different frequency bands, the E field, magnetic field, and power density have all these detailed specification there. This is for the unrestricted environment. The next one is for the restricted environment. Next. This is for local exposure. It's different from the whole body exposure. For the 10 to 6 gigahertz is this, all in the table. Next. And here the time exposure is all average over 6 minutes now. So this is for the upper tier restricted environment. Next. So this is for local exposure for the upper frequencies. And you see the this is ERL. ERL means you can measure with power density outside the body. And this is divided into 3 gigahertz, or then the 40 and 200. Then from 6 gigahertz to go to a curve, then go to 300 gigahertz to 20 and 100 megahertz, watts per meter square. So the details about averaging time and averaging area down below explained in the footnotes. So all these are in the standards. Okay, next. And in here, in the Annex B, we have a table B1 to indicate the safety factors. We are not just talking about exposure limit. It's the safe. How do you be safe? You want to have some safety margin to make it. So what's the safety factor? So for the low frequency, below 100 kilohertz for electrostimulation, we have a factor of 3 for the occupational exposure, for the 9 for the general public. For RF, we have 10 and 50 safety factors for between 100 kilohertz to 6 gigahertz. But for above 6 gigahertz for the epithelial, for the thermal pain on the skin, use temperature as a guidance, and the safety factors, they are smaller. And for upper tier, it's between 2 to 5. And for the lower tier, for the general public, is 10 to 25 for the epithelial power density safety factors. So all these things all explained in our standard. Next. So we have 5 annexes in C95.1, 2019. The first annex is on the how we come to this revision from the 2005 for C95.1. How do we combine with the low frequency standard of 2002 C95.6 into one standard? How do we make this two combine? And the Annex B talking about all the changes, why we change it, what's our reasons to document all the changes in the Annex B to explain the revision. And Annex C is identification of the levels exposure with adverse health effects, is a summary of the literature, especially I mentioned before, the C.8 is about the literature above 6 gigahertz to 300 gigahertz. And then Annex D, there are several practical examples, applications are listed in there. Then we have 1,510 references in the bibliography in Annex E. So with all that complicated standard, now we have, you see there are 6 standards listed here. If you click on this link above, you can go to IEEE standard. All these are under the IEEE GET program. That means they are all free. You can download that. If you download C95.1 2019, for sure, make sure you also download the Core 2, the first one, because we did find mistakes in figure 1 and 2 in the standard. So we made a correction in there. So make sure you download the both together. And the others, all in there. And thanks to the Department of Defense of the United States, the Navy, Air Force, and the Army, and they donate the money to IEEE, so that made all these standards are available for free to use. So you are welcome to download them for your use. Next. Okay, I just briefly mentioned about the assessment standards. There are currently 2 international organizations. They make this assessment standards. Okay, next. So I just select a few relevant to the devices, and 2 existing ones. The first one and second one, they're all dual logo standards, IEEE and IEC standards. The first one is the measurement standard for the handheld body-worn devices, and from 4 megahertz to 100 gigahertz. The second one is about the computational method, use calculations, and from 30 megahertz to 6 gigahertz devices, and they are existing for use. And for the higher frequencies up to more than above 6 gigahertz are still being developed by both IEEE and IEC, and one for measurement standard, one for computational standards are still being worked on. Okay, next. So I will just the last section is about some real exposure levels in terms of personal use or the base stations. Next. So this is about the 3G. You see the curves there. There are 3 different curves there, and for 3 different environments. You see the maximum power for a 3G phone like 250 milliwatts on the right. But for real use, like in the urban door, the thick black line, the peak at the 0.1 milliwatt was the people can able to use the energy to communicate with the base station. This is done by the Ericsson company, and they have used a lot of the data to come up this result. And you can see even below 0 dBm, less than 1 milliwatt is cover major communications use. So this is use a very small little power can use, you don't have to use all the way to 100, 250 milliwatts. Next. So how about the base stations? And this was published in 2012 of 23 countries. And on the average, global average is 5,500 times below the current IEEE limit. It's well below the limits of all 23 countries. Use 3G. Now we are talking about 5G. Okay, next. For 5G and 4G, here is the data from the Mobile Wireless Forum. It's for the 4G, you see this 100% is on top, and on 4G it's like 0.3% of the power. Most people using that power to communicate. And for the 5G, it's a little bit higher, like 8% percentile, but the mean value is still only 2%. So both 4G and 5G are also similar to 3G. A very small little power, you can communicate with the base station. Okay, next. For the base station, this is computation and also actual maximum and theoretical maximum. How far you have to be away from the antenna in order to be within the safety limit. The orange line shows curve, the circle shows within more than 5 meters, you will be within compliance. So you don't have to be worried about getting overexposure. Okay, the next picture is from 6 countries in the world and showing how many percent of the general exposures are below the IEEE guidelines. And you see the Colombia, you have a 0.37%, and the others all point some percent. Only Australia and New Zealand more than it's about 1 point some percent. So also very low in terms of 5G, currently from 1 to 6G range, the exposure levels. Okay, next. So with that, I want to conclude, and the RF exposure is very different from nuclear radiation. We have more than 70 years of research show only established adverse health effects of RF energy of above 100 kilohertz is due to thermal effects. International exposure limits the guidelines with large safety margins. Also, as assessment standards are available to protect provide the protection. For 5G new applications, new limits are in the frequency range of 6 to 300 gigahertz. We have new limits. And the local exposure, the reference limits, also the DRL, ERLs are derived from recent thermal modeling studies. And a large number of expert reviews have concluded that no adverse effects have been confirmed below the current international RF safety guidelines or special standards such as IEEE and ICNIRP. And most actual exposures are very low levels, as shown in the previous examples, are well below the exposure limits. So unnecessary worry can cause so-called nocebo effects. That is opposite from the placebo effect. Nocebo effect means if you believe something can hurt you, it will hurt you. So that can really affect your health. So with that, muchas gracias. Thank you.
Muchas gracias. Thank you very much, CK. So we have some minutes to end the session. So it's open to questions.
Yes.
While questions come from the audience, I want to highlight that the standard is available. El estándar está disponible para ser bajado de IEEE. As CK said, it is available from as a courtesy from sponsors, but as you know, standards, IEEE standards can be downloaded through Portal Timbo. I mean, the National Agency of Research and Innovation funds the access to IEEE Explorer, and in particular to IEEE Explorer standards. En Uruguay saben que se pueden bajar los estándares IEEE a través del portal Timbo, a pesar de que este está abierto.
But Rafael, you have to go to the IEEE GET program. The Explorer will not get you the free standard. You go to the GET program. If you are IEEE member, you can get for free easily. If you are not an IEEE member, you just set up a new account. Anybody can set a new account. My wife can set up a new account. When you set up a new account, then you can just download for free. Don't
Mhm.
pay any money for that. It's already paid for.
So it is a very, very interesting read. As CK said, it has 1,550 references. So it is a phenomenal work. So that has been done for uh, 15 years or more than 15 years. I mean, 15 years CK has chaired this committee, but it has a long story, as he said. So I have a question, CK,
Yes.
if you allow.
Yeah.
Um, I remember IGNIRP recommendations talk about aberration not only in time but in space. Because
Yes.
in I have very few experience measurement on broadcast transmitting station, but I did, and I measured electrical. I mean in VHF. Huh?
Yes. Yeah.
So something like uh, 190 megahertz,
Yeah.
and I find that the 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 electrical field strength it varied
Yes.
in the length of the body. So
Yes.
here, should we average? You say something about surface.
Yes, they are actually IEC standard 62232 standard, if I remember correctly, and they have a specified how you measure that. You can go through the scan of the body length, or whatever. If you are different position, you scan that cross section of the body to make the average of that for the whole body exposures. And for local exposure, like a very near field, then you have to measure within the exposed region to make some average. And so in terms of time averaging, now in the new standard, we have a revised both IEEE and IGNIRP is 6 minutes for the local exposure and 30 minutes for the whole body exposures. Yeah,
Yes, and to clarify that, that means, for example, if one person is exposed to the limit, exactly to the limit,
yeah,
he can be there for, say, something that, well, for the limit, he can be permanently, but in the double of the limit, he can be for
yeah,
15 minutes, and
yeah.
15 minutes he has to be uh, apart, inside with no exposure.
Yes, yes. If you have a 30 minutes, you can if 15 minutes, you can have a two times the limits above the limit if you stay within the 15 minutes. So this is all time average. This rationale because it's all relating to heating. If you expose less, you can expose to higher levels.
Okay, so how can a person, you invite people from Latin America to join the committee? How can they join? What is the load of work that is expected one volunteer is expected to dedicate
Yeah.
during a year?
Well, we have many people members from overseas, and we have a two times meeting in the past before pandemic. We all had two meetings, one in the winter, one in summer, for a physical meeting. But during the pandemic, we have changed to all internet meetings. So we have many more international participations through the internet. So really, like I said earlier, IEEE invite anybody interested in, and we open to people with some background, with some understanding, some expertise. We welcome people to join us. You just have to write to me, and I will forward you to our membership committee chairman to show if you really want to be interested, we'll put you on the committee. And when we come to discussion of the new standard, new revision, and people always to put into task groups, review groups, and to work on the reviewing the documents and come up, draft standard. People review that and give ideas and the comments. and this is all a group of committee work, and that's why it takes time to get a agreed document to be published. That usually take many years, like you said, 15 years from the previous version to now. And anyway, this is an open invitation to you guys from Latin America countries, and you're welcome to contact me. I'll show the last slide. I show have my email
Hmm. Here it
address
is.
there. You can just contact me. I'll put you in membership committee chairman to get you into our committee. But first, if you are interested, I can put you on observer. I can send you the minutes, the meeting announcements, so you can always listen in as observer or something. You're always welcome. Even you are not sure you want to be a member yet, you can be observer. I can send you the. Actually, we have all the meetings put in the IEEE ISIS website. It's an open minutes announcement. And if you really want to participate in a meeting, we will send you a link so you can join us. Even as an observer, you can just sitting in and listen to our discussions and all that. So we will have that available to anyone interested in our activities.
Fine. Thank you very much for letting us know. We have a final question from Fernando Hernandez, who is from Uruguayan URSEC, which is a Uruguayan FCC, similar to FCC. So he says the history from original version of IEEE standard is from Cold War. The values are very different from Russian ones. Nowadays, and for the future, the values are moving to IGNIRP, unifying the standard. What's your opinion?
Well, in the you're talking about the Russians, and they came from the Soviet Union time, and the approach of setting the safety standard is very different. For IEEE and IGNIRP, and we are very similar in terms of the scope. We both the guideline, IGNIRP guideline and IEEE standards, we are to protect against, we call it established adverse health effects, and IGNIRP call it a proven, it's health effects. So we're only talking about, we don't want to see anything proven bad to happen to humans. And the Soviet Union and the current Russian limits, they came from a different approach. They want to protect anything they have people reported can be health, can have effects. Whether it's proven or not proven, they want to be below that. That's why they always come up like 10 microwatt per square centimeter to be so low. And in nowadays, it's not possible. Not even nowadays, even before. For example, in Soviet Russia, you cannot apply that into the military because you just cannot do it. Your battleship cannot go out for any mission. And in China, I asked the Chinese Navy researcher, I said, can you guys use the Chinese low 10 microwatt limit for your military operation? He said, absolutely not. So that means that standard is not useful for practical use in some situations. So we need to base on scientific literature, scientific evidence, and this is what we have been doing, established adverse health effects. That's what we emphasize.
Excellent. Well, with this, we want to we clap hands at home, and we want to thank you especially because your participation is during the Thanksgiving holiday. And well, we wish you a nice Thanksgiving. Thank you for being with us and sharing this time at IEEE Eurocon 2021.
Thank you, Rafael. Thank you. Muchas gracias to all.
Okay. Thank you. Muchas
okay,
gracias.
Okay.
Thank you. Bye-bye.
Bye-bye.
We will end this session now.
Thank you.
Bye-bye.